this open there. Well, I just closed the wrong thing, yes. But that is good. Okay, yeah, thank you. So actually, I want to talk about not just the topic I announced, but also other stuff which is related to the expression problem. But it will still include the announced topic, which is about compositional and linear encoding of synthesized and inherited attributes as object algebras in Scala. Okay, so here's a little map of what I want to talk about. In the beginning, I will pretend that we don't know what the expression problem is and just state what it is. So we're on the same page there. And then I will talk about these three things that I recently realized about the expression problem. And this will all lead to a shameless plug about my ICFP talk later this week. So we start with the expression problem. I put a little mini-map in the top right corner of the slide, which is almost visible on the screen. Okay, so the expression problem is about the situation that you have tree-shaped data, and you want to consume it somehow, so you want to traverse it and do stuff to it, and maybe you have multiple traversals. So in that situation, there are two dimensions of extensibility that are considered by the expression problem. One dimension is to add more constructors that can show up in your tree-shaped data. And the other dimension is to add more consumers, like more functions, what you want to do with it. And this gives rise to this, this matrix of possible decompositions for our program that consists of lots of consumption of tree-shaped data. So we could do this by consumer, and usually we would say these are functions, and this is often called a functional decomposition because this is what you can easily do in a functional programming language. And then you can extend it by adding more functions. Or we can do it by constructor, and this is often called an object-oriented decomposition because that's what you can easily do in an object-oriented language by having one class per constructor. And then you can extend it in the other direction. But what we want to do is we want to be able to put our components in an arbitrary way into this pattern. So we want to just choose which component addresses which of the cells and merge them together however we want and keep extending this matrix. I think it's interesting that a similar kind of matrix also shows up when we think about data type generic programming. In data type generic programming, we often want to have most of the cells in such a matrix filled out generically, so that's the light gray ones. And then we only want to provide some source code for the black, well, darker gray ones. But we can still think about it with a similar kind of matrix. Okay, so that's the expression problem. And there is tons of research about it, mostly about solving it, but some people first extend it so they can solve it better. And I want to present these three things that occur to me in recent and ongoing and hopefully future research about it. So the first thing I want to talk about is the connection of a deep, shallow, and final embedding. So these are approaches for representing programs in programs. And since the programs we want to represent are essentially abstract syntax trees, this is also very much related to tree-shaped data. So final embedding is also sometimes called as polymorphic embedding or object algebras. That depends a bit on whose papers you read. So I'm personally all for polymorphic embedding. But there are also good reasons for the other terms. Okay. So these are the different papers introducing the thing in different meta languages, kind of. But of course, these, well, it's all subtly different, but we can ignore this for the purpose of this talk. So I think it was last year's keynote on this workshop, actually, where Bruno Oliveira talked about object algebras, and he gave a bit of a history of object algebras. And there, one thing I realized during his talk was that these kind of approaches for representing tree-shaped data, they work because by chance, programming languages tend to support extensible records better than extensible variants. So some languages with basic or no support for extensible algebraic data types still support extensible and very expressive record types. For example, in Haskell, data types are there, but somewhat basic, but we have type classes. And one way to look at type classes is as syntactic sugar for type class dictionaries, which are records with polymorphic components. So it's already somewhat fancy records. And then we can have multiple constraints on the same function. And the type checker will even figure out, or type inference will figure out which constraints we need. So this gives us a form of intersection types for these records. And this is, for example, heavily used in lots of Haskell libraries, like also the Lens library, which maybe some people know, where lots of clever stuff is computed just by figuring out type class constraints. In Scala, we have traits, which support mixing composition, so they are obviously about extensible records. And even in Java, we have interfaces, which are a bit like records. And then we have multiple upper bounds. So if we have a type variable, we can give it an intersection type as an upper bound. It's this crazy feature about Java no one knows. There's an ampersand type operator in Java, but you can only use it half of the time. So these languages and others, they have the support for extensible records. And one way to solve the expression problem is to somehow manage to encode your variants, not with variants, but with records. And then you can make use of these features. So I have a somewhat split view on whether that's good or not. So from the point of view of a programmer, this is great. Because I can solve the expression problem this way, and then it's solved, and it's fine. And from the point of view of a researcher, it's also fine, because I can publish papers about my solutions. But from the point of view of a language designer, I'm a bit annoyed about this. So what's going on? Why should we have, by chance, better support for records than for variants? I mean, they are the same thing, just dual or something. So shouldn't the languages support extensible variants in the first place, instead of forcing me to do this encoding? Well, let's look at this encoding a bit more. So the goal is to implement tree-shaped data using records. And to understand how that works, we first look at deep embedding. So deep embedding is a glorified name for just using tree-shaped data. So in this case, we have this, this is an algebraic data type in Scala. So we have a type for expressions, and then we have two constructors, one for literals, which are just an integer, and one for addition nodes, which have two children. So this is a very simple language which can express addition of numbers. And then we have an evaluator, which takes an expression as input and produces a number, and it does this by pattern matching. So if it's a literal, it returns the number that's stored there anyway, and if it's addition, then it will have recursive calls and then add up the results. So this is the obvious way to do this, I would say, in this Scala at least. And similar code you can write in Haskell, for example. Now, one interesting thing about this is that we have a type expression, and that there's only one place in the whole program where we pattern match on that type. Okay? And if there's only one place where you pattern match on the algebraic data type, that means that this program is in defunctionalized form. Okay? Defunctionalization is a process where you take a higher order program and you transform it, and then it consists of a data type and a function that pattern matches on the data type. And this could have been produced this way. So we can undo the defunctionalization and see where we end up. Okay, so here's the type, which is only a consumer. And what we can do is we can pull the consumer into the type. Okay? So in Scala, that means that we say, well, our trait expression actually has one method, which is called eval, and returns our integer. So instead of having the separate consumer, we pull the consumer into the type. And now we need to do something to the two case classes, and we can actually turn them into functions. So we can say that literals, we know that the only place where we ever deconstruct literals is in the pattern matching. So we can, instead of producing a case class, which we can pattern match on, we just write a function that returns an expression with the correct implementation of eval. So we pull the right-hand side of the pattern matching into the right-hand side of this equation. And then with addition, we can do the same thing. Okay, so now we refunctionalize the deep embedding, and what we end up with is shallow embedding. Okay, so there is tons of literature, especially tons of blog posts, about the difference and relationship of deep and shallow embedding, and at least I didn't never see mention that it's just defunctionalization and refunctionalization. Well, I think that's pretty cool. But we can go further. So I just said that the relationship between deep embedding and shallow embedding is defunctionalization and refunctionalization. By the way, defunctionalization is due to Reynolds from a long time ago, and refunctionalization is just the opposite thing, and you can read about that in this paper by Donvie and Millikan. So we can go further by considering the relationship between a program that does a fold over an abstract syntax tree and the final embedding. And it turns out that they are again related by defunctionalization and refunctionalization. So here we go. This is a program that does folding. So we have the same abstract syntax tree here. In addition, we have this algebra. The algebra has one method for each constructor of the abstract syntax tree, which is supposed to contain all the work that needs to be done when we see this thing in the fold. And we have the fold, which is defined by pattern matching, and then it calls the algebra methods. So probably no surprise for this audience. Now what we can do is we can again observe that this is in defunctionalized form because expression only is decomposed in the fold function. So we can pull the fold into the expression type. Then we need to change the literal by saying that instead of it being a data type, we now want it to contain the source code, the fold operation, and the same thing for addition. So again, we say that we see that addition is only decomposed in this one pattern match. So we pull the right-hand side of the pattern match into the right-hand side of a fold function that's embedded there. Okay? So this is the final embedding. And this allows us to, well, this was refunctionalization, and D and refunctionalization, they preserve the semantics, and they preserve everything about the program. So we can still do everything we could do before. So this is a tree representation. It's just a tree representation that does not use case classes, but uses this folding with an algebra kind of thing instead. So what I take away from this is that to study the relationship between all these embedding approaches, we should probably study defunctionalization and refunctionalization. And to be more precise, I think we should study it for Scala-ish languages. Because this works, but we also want to have the extensible traits and so on. So this is my takeaway from me realizing that it's all just defunctionalization and refunctionalization. So this was the first thing, which brings me to the second thing I want to talk about. Maybe I can take urgent questions if there are any. Can also not. Okay. So the second thing is about looking a bit more into detail about what we can do with this kind of encoding of things as algebras. And this is based on a paper we had last year at Uppsala together with Jonathan Prachthäuser and Klaus Ostermann. So it's about modular, scalable, and compositional encoding of attribute grammars in Scala. So why did we do that? Well, we had this idea of the two dimensions of modularity in the expression problem, and I think there's a problem with this picture. So we like to solve the expression problem, or some researchers like to do that, and it's very good. So if you solve the expression problem, this will help your paper get accepted. But I'm personally not super convinced that the expression problem, even in a program that consists mostly of tree traversals, the expression problem is enough, that solving it is enough to achieve modularity and achieve a scalable componentization. And the problem is that the expression problem stops in these cells. So the smallest unit of code we can have there is a 1-by-1 cell. And if we have a really big software, then that's still big. Okay? And the reason it's still big is that it needs to interact with other traversals. So it's not enough to say, in the end, maybe we just want to do one traversal. Maybe we're writing a one-pass compiler. So it's not enough to say we can decompose it into, 16 or something different things, because they are still too big. We want to decompose it much more. So we believe that to scale to large programs, these solutions to the expression problem need to comport components within a structure, which means that consumers should be able to depend on other consumers, they should be able to depend on context information, and we want to specify them separately, but then we want to still have them fused together so that we do less traversals of the tree overall. And the way we try to address this is that we looked at attribute grammars. So attribute grammars are a syntactic formalism for specifying really small components. It's just a bunch of equations, and they're kind of all written separately, and then they're often like wrangled together into one big source code that does the tree traversal. So we like that it's small equations, and we don't like that the target of the attribute grammar compilers the target source code does not actually show the modularity. So we try to express the same little components, but using algebras. So we first looked at bottom-up data flow, or we kind of realized that synthesized attributes which implement bottom-up data flow are kind of the same thing as this algebra stuff. So what do we have? In the upper row, we have attribute grammar things. So we have a grammar. It's a grammar for the same language we saw before. And we have equations. So these equations specify how to compute a value. It's also what we saw before. And then in the lower part, we have the signature. So that's the type of algebras. And an algebra that actually implements the evaluation. So what's interesting to note here is that in order to write the lower row, if you know the upper row, you need to look at all the left-hand side occurrences of nonterminals in your grammar. And for all of these left-hand side occurrences, you need to provide an equation because it's synthesized attributes. And they work like this. Okay? And that means that in our signature, we should also have one method for each of the left-hand side occurrences of nonterminals in the grammar. And then we can just take the right-hand sides of the equations and copy them down to the right-hand side of the methods in the algebra. Okay, so that's how you do synthesized attributes with algebras. Now, what turns out to be much harder, or somewhat harder, is to support top-down data flow. But of course, you need that too. So it's not enough that information bubbles up from the bottom, but you also need to get information from your context. And the way we did that is that we looked at the same grammar, but now we have equation for an inherited attribute. So this attribute computes whether the current node is a left child of an addition node. So you would need that if you write a pretty-printer and you want to avoid parentheses or something. Okay, so it's actually can be a smaller component in a different traversal. And the basic idea here is that we look at all the occurrences of nonterminals on the right-hand side of the grammar productions, and we need an equation for each of them. Okay, and this means that a signature for inherited attributes should have a method for each of the right-hand side occurrences of nonterminals. Okay, that's the crucial step here. And then we can, again, just copy down the right-hand sides of the equations to the right-hand sides of the algebras. So the key idea is to create a signature, which is kind of the grammar turned around, where we look at the right-hand side of the grammar production instead of the left-hand side. And then it's just a signature. So if we ignore the upper row, then the lower row, this is just an encoding of some tree. Okay? The signature doesn't look different than other signatures. Yes?
Can you say something about the types of N1 and 2?
In the algebra? Well, in the signature, I guess. Yes. So the question is about the types of add1 and add2 in the signature. So the signature is generic in the type we want to eventually compute. So the E type parameter stands for the type of the attribute we want to compute. And that means that add1, it takes add1 corresponds to the non-terminal E2. And at this point in the tree traversal, we have information about our context, and we don't have any information about anything else. So the E, so it's a function from E to E, and the E argument, this is the information we take from our context. It's information about an expression, so that's why it's called E, because E2 occurs in the production for E1. Okay, so the parent of E2 is also an expression, so we have expression information, which is what the E stands for. And then the E we return is the information we compute for the E2 expression. Well, we compute to be used when traversing the E2 expression. So this kind of code will be run when we see an addition node when going down before we recurse into the first child. I think this will become a little bit more clear later, because later we actually have different letters for all these E's, and then it's maybe easier to talk about it. Okay, so maybe the interesting thing is that for add2 we have two inputs. We have E and E, and the first E is the context that we get from above, and the other E is the information we get from the E2, because now we did already traverse the left-hand side child, And now we can access information from that, and we can also access information from the context just before we recurse into the right-hand side child. Yes?
So does it make the order explicit in each signature, the traversal order?
Yes.
And is it
So the question is the traversal order explicit? And the answer is yes.
and explicit basically? I mean, so usually you don't really care about the order to traverse and to evaluate attributes. And,
Okay, so you're asking that usually.
one order might be more efficient than another order. But if you fix the order already, then you might lose the potential for optimization.
Yes, so you're concerned that since we fixed the order already in the types, we cannot choose a clever order for traversing the tree. And I mean, that's correct. So in the context, so we were thinking of one-pass compilers where there is an order fixed anyway, because we have to traverse the abstract syntax tree in the order it's written in the source file. Okay, and for this scenario, this is not an issue. If you want to have an arbitrary order, then it's, at least to me, somewhat unclear how we would encode that in a Scala type system, but probably possible anyway. Because then, if we support an arbitrary order, then we still would want to somehow compute in a type system visible way a good order, maybe with not too many traversals or something, which is the kind of thing that attribute grammar compilers do. And of course, it would make sense to also support this here, but we don't. Okay? So what we gain by encoding both synthesized and inherited attributes as just signatures and algebras is that we can use the same composition mechanism for both. So the way we assemble many synthesized and many inherited attributes into one traversal is that we compose all the synthesized attributes, and we compose with the same mechanism, just on the different signature, all the inherited attributes. And then we assemble just one synthesized attribute that does all of the synthesized work and one synthesized attribute that does all of the inherited work into one pass traversal. Okay, so how does that work? First, we need a bit of stuff because it's not provided by Scala. So in order to implement composition, we need better intersection types, essentially, because we would like to merge information computed by different attributes. So we have these little traits that just have one method, which is our interfaces for the attributes. So has value is the interface for something that supports a value attribute, and has left is the interface for something that supports a left attribute. And now at some point in our in the traversal, we would like to merge a value that has left and the different value that has value into one thing. So we do this with this mix function. So it works for arbitrary types, A and B, provided it's actually implemented for these types. So this is an implicit argument, which is similar to type class constraint in Haskell, if you know Haskell better than Scala. So it means that whenever this function is called, and there is no explicit argument provided for the second argument list, then the Scala compiler, the type inference, will figure out a value of mix AB, given all the implicit values in scope. And if we manage to do that, then we can take an A and a B and turn it into an A with B. Okay, so in Scala we have, so A with B is the intersection of A and B. It has the interfaces of both. In Scala we have this on the type level, and we have it statically, but we don't have it at runtime. So it would be nice to just have this as an operator in Scala, some ampersand thing or something, but we don't. So we wrote this function, so that's easy. The hard part is to, where do we get all these implicit values into scope, so that for all the A's and B's we have, we actually can mix the things together. And we did that with an implicit macro, which is a pretty cool thing, I believe. So it's an implicit definition. That means that during implicit resolution, it will be considered by the compiler if it's in scope. And it actually works for all A and B. So for all A and B, it returns a mix of A and B. And the way it can do that is that it's also a macro. So it's just an implicit and a macro at the same time, which means that during resolution. This will be hopefully considered late. So if users write some implicit definitions that have a more specific type, it will be hopefully considered earlier. And then when nothing else works, then this macro will be called. And the macro actually is implemented by this thing, which take these weak type tags. So a weak type tag is a description of the structure of a type. So inside the macro, we can do, data type generic programming to generate an implementation of our intersection type. So we do something like new A with B, and then we do def this and def that. Okay? Def value and def left in this case. And we kind of forward to the other things. So I think that's so far I think this is a pretty convincing story for how to extend language in a type-driven way. There is a bit of issues with all the contexts and crazy things there. So the ... is pretty complicated. But if we ignore that, I mean, we manage, so whatever. I think that's pretty nice. Yes?
I'm just wondering what, are you expecting in the mix that I'm saying essentially arbitrary?
So the question is whether we support arbitrary A and B, as I admittedly claimed.
If that's the case, I was just wondering if A is into B is string, what is the meaning of A and B?
Yeah, okay. So you're asking about what if A is int and B is string, how can we mix it together? So I guess we can't, because there is just, so I guess it already wouldn't type check. Like we get int with string, and I don't think we should have a value of that, maybe null or something, maybe not even. In practice, we are using this for these kind of has value, has left style types, and there it works, and there it's also clear what we want to do. And I guess that it's not possible to extend it. I mean, there are theories of intersection types where you can intersect arbitrary things. So the keyword there is pure subtype systems, and G-deep and similar things. But I don't think we can hack this into Scala this way. Yes, oh yeah, sorry. Yes, you're right, we can form the type. I mean, we can say int with string, I can write that down, that's fine. But it doesn't have any inhabitants, so I can also not generate not generate terminating source code that produces such an inhabitant. So, I mean, I think that's fine. We don't need to intersect non-class types here. What's annoying is if we can't express this or we don't know how to express this. Maybe we just need to say A is less than object or something. So probably you could just solve this. Yes. So while you are at it, it's also pretty slow because we just forward all the calls. So that should also be fixable by just copying the data or something. But it's all a bit hairy because we want to preserve the exact evaluation order and the order of side effects and so on. So this part of the library could use some expert makeover, kind of. Okay. So I promised that we will understand all the type parameters better. And the reason is that now we give them different names. And so we have this E, C, and O. And to understand this, we need to imagine a tree. And we need to think about where we are in the traversal and what we just seen and what we will see next. So the idea is that the E parameter stands for the information we get from our children. And the C parameter stands for the context we get from our parent. And then we compute information for the current node. Okay, and this explains why a literal, it takes an integer because that's stored in the literal, and then it takes some context information, it doesn't have any children, so it just produces the output. And addition, it doesn't have any data stored directly, it just has two children, so it gets some E information, and then it gets some context and produces some output. So this works for both synthesized and inherited attributes. It's just that you need to turn the tree around for the inherited attributes. Okay. So now with this more descriptive type for signatures and with our mix thing, we can implement compose. So this is just a type. So we take two algebras of arbitrary types, except that we have this one constraint. The one constraint says that the context of the second algebra contains at least the information, I'm not sure about that list, contains the information that's in the context from the first algebra together with the output from the first algebra. So again, we see the fixed order here because the output from the first one is merged into the context for the second one. So it's available for the second one. And then, yeah, what I just said, okay. And then in the output, we are computing, so the first parameter is what we expect from our children, and we expect enough information to run both algebras. And we only need a context for the first algebra, because the context for the second algebra is formed automatically, as I just explained. And we compute the output of both algebras. Okay, so here we can talk in the type system about required and provided interfaces of our algebras. And this is necessary because this is a child and this is a context and so on. We need to be explicit about that. So we couldn't use some built-in mechanism for doing that, but we need to make it explicit and write the correct constraints ourselves. Okay, so after we composed all these algebras together, we want to assemble. And when we assemble, then we take, again, two algebras, but now it's with the same type parameters, but for different signatures. So we take one algebra that describes all the synthesized stuff we do, and one algebra that describes all the inherited stuff we do. And we merge them together into one algebra that computes a function. Okay? So maybe some people were thinking, why are they not using a reader monad all the time? So we are using a reader monad after we assemble everything. Here's our reader monad, okay? We take the context, so in the end we compute one value, which is just a function, which takes the context that is to be put into the root, and then it does the traversal, and it returns the new context for the root together with the output for the root of the tree. Okay, that's the traversal we do. And the reason we are not using the reader monad earlier is that we want to have composable components. And if you start having functions, then it's much less clear how you can compose them. But we just use the same mechanism for representing the inherited and the synthesized attributes. So we can use the existing techniques for composing synthesized attributes also for inherited attributes, because it's not functions, but it's just a collection of methods in an algebra. And then, when you are done writing your program in the final assembly step, you get this function, which you then can call on the initial context for the root of the tree. Okay, so what we achieve here is that, what we achieved there was that we realized that object algebras correspond to synthesized attributes. We extend object algebras to also support inherited attributes using this trick of looking at the right-hand sides of the grammar productions. And this allows us to assemble multiple algebras to support L-attributed grammars. Okay, an L-attributed grammar is a grammar where you can look at your children and the context and the neighbors to the left. So it's exactly arbitrary one-pass compilers. So we actually evaluated this a little bit by writing a one-pass compiler. So we took a one-pass compiler, which was written not by us for a subset of C. And this is the left-hand side. Here's a snippet from that compiler. It's 800 lines of Java code in one file. So we take this as big and entangled. We kind of marked up in color what the concern of the different lines is. So this is just one method. It's a recursive descent parser that is the blue stuff, and the colors, this is computing all kinds of attributes. And then we disentangled that into 25 files with a total of 1,600 lines of Scala code, which we believe is much more modular. So each of the colored things on the right-hand side is one top-level declaration. One. And they could be in different files. Or since we have 25, I guess they are in different files. And they are compiled separately by the Scala compiler. And it's type-checked that they all work together. Okay? So we're pretty happy about that. So it actually worked, we believe. So now comes the keyword from the title of the talk. So the way we set up this compilation was so that, the way we set up the encoding of attribute grammars as object algebras was so that The attributes are defined and type-checked separately, as I just mentioned, in our 25 files, but also so that the Scala code size generated is linear on the size of the attribute grammar specification. So we carefully looked at all the lines that you need to write or that are partly generated by tools, and they all come from a certain artifact in the attribute grammar specification. So you need 1 line per equation and 3 lines per dependency between this and that, and there are so many lines per non-occurrence of something on the left-hand side, and so on and so on. And we believe this is pretty important if you want to have an actually usable system, because you don't want it to explode for a bad input, kind of. Another thing that was really cool, we believe, is that it's compositional in the sense that each attribute grammar artifact is represented as a scalar value. So an equation is an object, and a grammar is a tray, or for some meaning of artifact. Anyway, what this gives us is that we get some additional benefits. So what we wanted to have is we want to implement the attribute grammar system at all, and we want to have it be extensible. So we still want to solve the expression problem, and we just do because it's object algebras, and traits are composable and so on. But in addition to that, we also can do some forms of generic programming, because some things that are second class in an attribute grammar are now first class in our encoding. So for example, if you want to have a list in your grammar, like a list of statements or a list of expressions, then in attribute grammars, you need to duplicate all the things about lists. But in our encoding, we can talk about that. We can say that we want to have a list of nonterminals in our grammar, and we can say that we want to have list equations, and then we can have an attribute like compute the length of the list, and it works for different lists. All the things you would expect as a programmer, but which is actually not per se available in attributed grammars. And we get that for free, just because it's encoded in a decent language. Okay? And it's encoded in such a way that the meaningful things from the input are actually values in the end, are actually first-class entities in the output. So if you do encoding, try to do it like this, because then you get these things for free. So our Scala experience, good things. Well, traits and static mixing composition is good. Type inference is great when it works. Implicits are good because they give you an extensible type system. Macros are good because they let it extend without, well, by just saying what you want, kind of, instead of jumping through hoops to get implicits to build up to something. And especially, well, implicit macros are good. So we really like the interaction of these two features. Bad, well, we missed this introduction form for intersection types, so it would be good if that would just be provided. Type inference is pretty annoying when it fails. Now, well, it's undecidable, so it sometimes fails. And the details of macro programming are somewhat horrible. So I hear the macro programming story in Scala is constantly changing, and I have to admit that I don't know how it is right now. But a year and a half ago when we did that work, macros were like plugins to the compiler, and they were compiled against the same data structures as the compiler used internally, which is pretty powerful, but also not the easiest thing to learn. Also not the most stable thing to use. So what I took away from this is that some of the OO-inspired features of Scala are very good for modular, scalable, and compositional encoding, but we don't actually need full object orientation. So we don't use any implicit self-recursion. We don't use any side effects ever. So there are things in Scala which we don't care about at all. Okay, this brings me to the third thing I want to talk about, which is ongoing work together with Jonathan Prachthäuser, Paulo Giarusso, and Klaus Ostermann. And it's the idea that, well, if you look at the expression problem, then it's pretty nice. It has driven lots of research. Some of the solutions are actually usable, and it occurs all the time in practice, at least to me. So every time I write a little interpreter for a little language, I'm annoyed that there is no perfectly usable solution for the expression problem built into my implementation language. So we thought, why don't we just turn it around? Why don't we apply duality to the expression problem to find the co-expression problem? So let me just reiterate what the expression problem is. Data types are defined by constructors, and functions consume data values by covering all of the constructors. And the question is, how can we extend both the set of constructors and the set of consumers in a modular way? So by dualizing this, we can say that a co-data type is defined by destructors, and functions generate co-data values by covering all of the destructors. And then the question will be, how can we extend both the set of destructors and the set of generators at the same time? Okay, so this works. I mean, I just stated it. So what do we do next? So we actually wrote a paper about it that was rejected from this conference. But I tell you a little bit about it anyway. And so we have a bunch of questions about this. So a set of questions, one is about the impact of this idea. So where are the real instances of the co-expression problem? So when you write programs that use co-data, maybe just records or maybe some kind of transition systems or something, do you need extensibility? Is it actually missing, or is this just some academic, yeah, we dualize this and that, but no one cares? So what we believe is the answer is that most programs using co-data don't actually use recursion. So that's why it doesn't show up. So the expression problem is only hard if we consider recursive variants. If you have a data type without recursion, then we can use something like data types a la carte relatively easily, and it's just no problem. We don't need any functors and stuff. And maybe the same is true for the co-expression problem. And we need to look at the specific domains of software where this actually shows up. And the next question is, can and should the co-expression problem guide research on co-data representation in a similar way to how the expression problem guided research on data representation? And I guess that depends on whether the impact is there or not. So we also thought about the solutions, and we believe that it should be possible to categorize solutions to the co-expression problem in these three categories. So we believe that some solutions to the expression problem just also solve the co-expression problem. Okay? And there are other solutions that can be dualized to solutions of the co-expression problem. So we have like corresponding solutions that are just dual, just like the problems are dual. But then what I find most interesting is the questions, are there also solutions that are unique to one of the problems? And I'm interested in this because I believe it points to asymmetric support for data and co-data in programming languages. Because it should be just dual. And if the problems are just dual, and data and co-data is just dual, then it should be possible and feasible and easy and at least thinkable to have equally well-supported data and co-data. So that if I can solve one of the problems, I can do the dual thing to solve the other problem. So there's one paper, if you care about this, you should read, which is the paper about the expression lemma by Lemmel and Wipacek, I guess. It's from 2008, so it's not even that new. So we believe it formalizes the semantics aspects of the expression problem. That's what it says to do. And we believe it also covers the co-expression problem just so. But we don't fully get it. So this kind of covers the semantic aspects. It uses category theory and everything just dualizes, and bam, there it is. Okay? So our question is, in what setting should we study the syntactic and engineering aspects of the co-expression problem? So knowing how to dualize something in category theory doesn't mean that we know how the programming language should look like, the syntactic aspects, and it doesn't mean how we should actually benefit from some extra modularity we might get from solving the problem. That's engineering aspects. So it's not enough to draw a diagram and reverse the arrows. We also need to understand it. So what I take away from this, ongoing or future research, is that to investigate the relationship of the expression problem and the co-expression problem, we should try to use a language with symmetric support for data and co-data types. Which is the last thing I want to talk about. A very simple language for symmetric support for data and co-data. So this is a little advertisement for my ICFP talk later this week, and it's based on the paper together with Julia Trieflinger and Klaus Ostermann. So we built this little language that is very simple and very symmetric, and in the future we want to use it to study this kind of thing I talked about today. So the language has data types, and they are defined by listing all the constructors. And then it has co-data types, and they are defined by listing all the destructors. And both the destructors both the constructors and the destructors, they can have arguments, even though head and tail happen to not have arguments, but they could. So for example, we can also represent functions this way by having an apply destructor which takes one argument. And then we have first order functions. So they're only on the top level, so no lambda stuff. And they are defined, well, you can either define them by having equations that pattern match on data, or you can also define functions by having equations that co-pattern match on co-data. So co-pattern matching is inspired or was introduced by Abel and colleagues in a paper at Popple 2 years ago. So it's the dual to pattern matching. Okay, it looks a bit like defining a method, but it's a FP way of defining a method if you want. Okay, so I hope it becomes syntactically clear that this is very symmetric. It's also very simple. It's purely functional. There are only simple types. There are no first-class function, no case expressions, no co-case expressions, no local variables, no nothing. So it's really just what you saw on the first slide. However, even with this very simple language, we have some first results. So we have support for full defunctionalization and refunctionalization. So we can go back and forth between a program that only uses data or a program that only uses co-data completely automatically. It always works. It turns out that programs can be written as matrices by just leaving out some new lines. And then D and refunctionalization correspond to matrix transposition. And they actually both correspond to matrix transposition. They also obviously inverses of each other this way. And these matrices also look like the matrices we have seen for the expression problem and the corresponding matrix for the co-expression problem. Yes, so more about this in the presentation at ICFP on Tuesday. It says there. So to summarize what I told you, I talked about stuff I realized about the expression problem, partly novel, maybe partly not. I talked about these three things. The first thing was that the relationship between different embedding approaches for embedding of ASTs kind of is by defunctionalization and refunctionalization. The second thing was Scala is a nice language for doing advanced embedding things, but we don't actually need all of it. And the third thing is we would like to dualize the expression problem to the co-expression problem. And these three lines of research, they all pointed us towards we need symmetric support for data and co-data. We need a simple language which you can fully understand, which gives us this symmetric support so that all the things that work in our head actually work in the syntax and become completely apparent. Thank you. So the question is, what is the speed of the Scala version compared to the Java version of the one-pass compiler, I guess? It's insanely slow. Yes, our version is insanely slow. Yes. So follow-up question, why? So we believe the main reason it's insanely slow is our implementation of mixing composition. So our implementation of these intersection types where we just forward things. But we didn't look into it deeply enough to say that with certainty. Yes?
So you used Scala for this. Can you talk about like what kind of things would you need in other languages to do this? Like, could you do the same in Haskell or yeah? So you had a slide with some different things you could know from Scala.
Okay, so the question is, what Scala-specific things did we use and what would we need in other languages, for example, in Haskell? So I guess, yes, we could do that in Haskell. So we have some versions of this kind of thing in Haskell too. Then there are lots of little differences, of course. So this kind of thing, it boils down to how you, okay, so it's kind of hard to say that one language is better or worse than, because in many languages it's possible if only you generate enough code. Sorry. If only you generate enough code, then it just works. So, so if you want to compare this, it's kind of unclear what the how to evaluate how well it works. because it's based on having these macros and generating certain amounts of boilerplate code and so on anyway. So yeah, so if your type system is up to expressing these constraints, well, let's say every Turing complete type system certainly is, then I don't know what it means to say does it work or not. What you do need is some form of these kind of extensible record types. But in Haskell, the type classes that would just work.
So you presented attribute grammar as a nice way to describe traversal or tree structure data. And I'm wondering how would that also work for graph shaping, or at least acyclic graphs? And would there be a way to implement that into your encoding? Maybe use that as a way to describe graph transformations, something like that.
Okay, so the question is whether we can generalize the way we treat trees also to graphs, or maybe at least to acyclic graphs. So, the way to generalize this is to add more type parameters, and I guess that would work here too. So at least for acyclic graphs, we could have we could add more type parameters for the data we store for nodes we have seen before. And then the whole handling of we have seen this but not that would have to be outside of the algebra. It would be in the whatever code actually calls the algebra methods. So in the fold, for example, or in the parser if you're writing really a one-pass graph transformation. And then that should just work. So you would just call different methods kind of when something is cached or not.
So some form of memorization where you
Yes, so one way it would be to have a transparent memorization, where you compute the same result as if you would unfold the acyclic graph to a tree, but you might compute it faster. But I expected that you also want to actually observe the sharing, or at least that's the hard part usually. And then you probably want to have more methods in your algebra. So you want to have a method for I see in addition and I've seen the left-hand side before, and a method for I see in addition that I've seen the right-hand side before, and a method for I see in addition of both sides before. Something like this. And then you could have some different data there because you use a different type variable. And then that would be, so I think this would correspond to representing your graph structure as a tree. And in the tree, it's represented whether something is shared or not. And then it's just the algebra version of that. On the other hand, I mean, we could also think of representing graphs using co-data, of course. By talking about if we are at a node, we can go to the neighboring nodes, and that's our observations. And then we are in this co-expression problem territory again.
so you said that for the code expression problem, you said that in most cases it should be very easy because there's no recursion problem. I didn't understand it. I mean, when you have some kind of co-recursion, where you find this? I mean,
Yes. Yeah, so you're asking about why I said that it seems that in many cases where co-data is used, it's used without recursion, and then the co-expression problem is not really interesting. So, I mean, every time you have an object with a bunch of methods, that's co-data. And if none of the methods return the same type, return again an object with these methods, then it's a version of co-data without recursion. I mean, the same is true for the expression problem in data. So most forms of data are just like Booleans. Okay? It's probably the most often used data type. It has these two constructors, there's no data stored in there, there's no recursion. And it would be interesting to extend it. It makes sense to ask, can we have true, false, unknown? And we can, because we use something like maybe Boolean or something. So we can extend it, and it's easy-ish because it does not support recursion. Okay, because we don't have any recursive calls in our function that we need to worry about. And now there is one important use of recursion or co-recursion with co-data, which is if you write an object-oriented application, then it has state. And one way to understand the state is saying that, oh, actually, every time I call a method, it also returns a new copy-ish thing of the object. Okay? And of course, most object-oriented applications, they are like that. They do that behind the scenes, if you want. And then we could talk about extension. And then it turns out that there are hard problems when we try to do this, which I think maybe are related to the co-expression problem. So if you want to type this, it's already kind of hard, because what's the type of this implicit self-returning thing? How do we store all of them? If we have such an evolving system that just returns a copy of itself every time, I think this comes up in functional reactive programming also, then how can we add something in the middle of it that changes the type? And how can we still store the whole structure in the same thing? Jonathan, one of the colleagues I'm working with on this, he's specifically interested in looking at this kind of time axis. So in object-oriented programming, this returning a new copy of yourself is related to time passes, because with mutability, you can only go forward, kind of. So it would be interesting to take an object-oriented system and add a method in the middle, and then see how we can do that while the system is running. So this is a twist on this. We believe that's a twist on this situation.